This video is going to go over some of the basics of our gas laws, covering Chapter 8 of the OpenStax textbook. Um, and a couple things to keep in mind as we talk about gases. The first thing is remember that solids and liquids exhibit different physical and chemical behaviors. So the identity of a solid or a liquid is going to affect what the physical properties and the chemical properties of that substance are. However, with gases, the physical properties are going to be the same regardless of the chemical makeup. So three gases that chemically react very differently, helium, hydrogen, and fluorine, are all going to have the same physical behavior based on our various gas laws. And and we can look at gases, and when people study them, they find out that there's relationships between certain physical properties that have emerged, and we can use four variables to really define our gas and explain a lot about it. And those variables are the pressure, volume, temperature, and then the amount, which when we talk about amount, we're always talking about moles. Um, it's important to think about units when we talk about gases. So temperature, we always want to use Kelvin when we're discussing temperature. Um, and volume is typically in liters when we talk about gases. So the first relationship we're going to look at is that between pressure and volume. And that goes back to what's known as Boyle's law for Robert Boyle, who discovered this. And what we're looking at is this relationship of what happens to the volume of a gas if we apply pressure, or alternatively, what happens to the pressure of a gas if we change the volume. And the key here is holding all other variables constant. So we can look at this, and to look at it, I'm going to use this PhET simulation. You can see the website up top, phet.colorado.edu, and we can look at this, and we have this nice simulator, and this is a nice box. In this box, we can measure the pressure, we can measure the temperature, and I can start off just by using like a bicycle pump, and we're going to pump in some gas molecules. So there's our gas molecules. And again, once those gas molecules are in, you can see we have a pressure. That pressure comes about from the collisions of all of these gas molecules on the surface of the container. And so now what we want to do is we want to say, if we were to change the volume of our system, what happens to the pressure? So again, here's our pressure. So what I'm going to do is I'm going to keep this number of particles constant and keep our temperature constant. And I'm just going to make our container smaller. So our pressure's starting at 16 atmospheres. And if I shrink down the size of my container, so volume went down and pressure's going way up. And so we see this inverse relationship. And why is that? Well, if we made our container smaller, there's going to be more collisions of those gas molecules with the outside container. If I make my container bigger, the pressure is going to go way down, right? Because there's less collisions, there's more space for those molecules. So we're able to see this relationship. So we can come back, and when we look at this, what happens to the volume of gas as we apply a pressure? And what we're seeing is this um, pressure and volume have this inverse relationship. And this is similar to the experiment that Boyle had done in the 1600s, where he changed the pressure of a gas and measured the volume. And so what we're seeing here is changing the pressure by adding mercury and seeing how that gas was compressed. And one of the interesting things about this is if you took some sample of a gas and you started with a volume, measured the pressure, and then increase the pressure, measure the volume, increase the pressure, measure the volume. So temperature is the same and the number of particles is the same. If you multiply the product of pressure and volume, you end up with a constant. You always get the same value for that system. And so what Boyle said was the product of pressure and volume is equal to some constant K. Now, this This is Boyle's law, and what we're going to see is there's a more useful form of Boyle's law, which involves two sets of data, because what the value of this is not so much in solving for K, but in using this to predict a new system. So for example, if we're starting out with this first line, we have a volume of 117.5 cubic inches and a pressure at 12 inches of mercury. We can now say, well, if I were to increase the pressure to 32 inches of mercury, what will the volume be? And because we know that in both cases, pressure times volume will give us the same value, we know we can take this value of K here, divide by the pressure, and solve for the volume. And so what we've done is derived a slightly different equation where we have P1 V1 equals P2 V2. And all we're saying is under the same system, the initial pressure times its volume has to be equal to the final pressure times its volume. And this allows us to find new volumes or new pressures if we think about what's going to happen to those. So let's look at an example of this. So in our example, we have in an automobile engine, the mixture of gasoline vapors and air in a cylinder is compressed from 1 atmosphere to 9.5 atmosphere prior to ignition. If the uncompressed volume of the cylinder is 410 milliliters, what is the volume in milliliters when the mixture is compressed? So this is a good example of an application of Boyle's law. We're holding temperature constant and we're holding the number of moles of gas constant. We're going to be changing the pressure. We go from 1 atmosphere to 9.5 atmosphere. And so what we wanted to figure out is what happens to the final volume. And we should be able to predict it. If we're increasing the pressure, our volume should go down. Right. So let's see what happens. When I set up these problems, I like to first write out what we know. So in this case, P1 would be 1 atmosphere, P2 is 9.5 atmosphere, volume 1 is 410 milliliters, and we're solving for volume 2. So again, P1 times V1 equals P2 times V2. So we can go ahead and plug that into our equation. P1 V1 equals P2 V2, 1 atmosphere times 410 milliliters is equal to 9.5 atmospheres times our final volume. We can divide by that by the pressure, and we find out the final volume is 43. So if we increase the pressure from 1 to 9.5 atmospheres, our volume has gone from 410 down to 43 milliliters. Okay. Our second gas law that we want to look at, second relationship, is that between volume and temperature. So if we hold now pressure constant in the moles, how does changing the volume affect the temperature of a gas? Okay. And so again, we can use a simulation to sort of help us predict this. And I'm going to go ahead and go back to our same PhET simulation. We're going to put a bunch of gas molecules into our system. And now we want to hold pressure constant. All right, so we're going to hold pressure constant, and we're going to allow volume to move. So volume can go up or down, but pressure remains constant. And what I'm going to do is I'm going to heat our system. And as we heat up our system, in order for the pressure to remain constant, what has to happen to the volume? So we're going to add some heat, and as soon as we do that, notice the system has to get bigger. So increasing the temperature, our volume has to get bigger in order for the pressure to remain the same. And why is that? If we're increasing the temperature, the molecules move around faster. So the only way they can avoid increasing the pressure is they have to take up more space. If we go the other way, we can cool it down. If we cool it down, the volume gets smaller, right? And the key takeaway from this is volume and temperature are directly related. If we increase temperature, we increase volume. If we increase volume, we increase temperature. And so we can come back and say, what happens if we put a balloon in the freezer? Well, that's decreasing the temperature of the balloon, so we're going to decrease the volume of the balloon. Charles' law states that the volume of an ideal gas directly related with temperature. We can put that in a different form. And the other neat thing that Charles did was he was able to study the volume on the y-axis and temperature of a variety of gases, so helium, methane, water, hydrogen, and he studied as you change the temperature of these, what's their volume. And interestingly, if you then take these data points, we have a nice linear relationship, nice direct relationship. And if you extrapolate down, they all end up at the same point. And this question of what happens if you extrapolate to the point where your volume is zero, where your gas takes up no space, what we see is they all come to this negative 273 degrees Celsius. And this negative 273 degrees Celsius is what we refer to as absolute zero, right? So absolute zero, this is where this Kelvin temperature scale really comes from, and saying we can't go below this temperature because what would it mean for a molecule to have zero volume? Right? At absolute zero, gases have no volume, so we can't actually get to that. It's a theoretical value, but we can get pretty close. Okay, so back to Charles' law. If we think about Charles' law, right, we said volume is proportional to temperature. We can write this in a slightly different form. Volume is equal to some constant times temperature. And then we can write that as the volume divided by temperature is equal to a constant. And the reason we're rearranging this is we can get to a more useful form where we can use to predict a new system, just as we did with Boyle. And we could say, in this case, Charles' law is V1 over T1 equals V2 over T2. Now, the thing to watch out for and be very careful about is the temperatures in this equation must be in Kelvin. So a lot of times we're given degrees Celsius, so we have to convert to Kelvin by adding 273 to the Celsius temperature. So let's look at an example. A balloon contains 20 liters of helium at 25 degrees Celsius. What will the volume of the balloon be if the temperature drops to 0 degrees Celsius? And this is a good problem to really indicate that we have to go to Kelvin, because you can see one of our temperatures is 0 degrees. And if that's T2, we can't have T2 on the bottom of a fraction being 0. All right, so we have to convert this to Kelvin. And we can go ahead and do this. V1 is 20 liters, T1 is 298, T2 is 273. What is that final volume? And we can see the final volume in this case ends up being 18.3 liters. So make sure you can work out that algebra. If you have any questions, please let me know. Thank you.